Ladies and gentlemen, President Joseph E. Aoun.
Good afternoon. Let me repeat one more time. Good afternoon. Well, I'm very happy not to introduce David. You all have his bio, and I invite you to read it. But let me mention that it's a special pleasure for me to welcome him because he used my domain. I'm a linguist, and he relied on computational linguists and natural language processing specialists and parsing specialists. But more importantly, I liked very much Watson because, as a matter of fact, whether some of you know it or not, I owe my job to Watson. And without further ado, let me show you what I mean by that. David was telling me that some people are afraid of machines. You can see that we embrace them and actually we replace them. It's the other way around. We don't believe they are going to replace us. We are going to replace them. So without further ado, David Ferrucci.
Thank you.
Thank you, David.
Well, let's see. Thank you so much. It's really a tremendous pleasure to be here and to have an opportunity to talk to you about the Watson project and what I think the implications of what we've accomplished with Watson are. But I think where I'm going to start with, though, is to kind of talk a little bit about what Watson is and what it isn't and how we actually did what we did. And then once I do that, I'll talk to you about how I think it can apply in the real world outside of the game of Jeopardy, for example. Why did IBM even do this? And some people look at what happened from the beginning of this and says, why did IBM even really get involved in something like this in a game show? Well, I think we looked at it and we thought, this is an opportunity to really advance science. And one of the things that's exciting and things that we've done in the past, like with the chess program, Deep Blue, that beat Garry Kasparov at chess, is to identify a challenge that not only advances the science, not only is relevant to our customers and what we do from a technology perspective, but also sort of reaches out to the broader audience and sort of wows them, gets them to scratch their head a little bit and say, where is this computer technology really going? How does this relate to society? How does it relate to me? And of course, inevitably, this brings in the whole subject of artificial intelligence. And what does computer intelligence really mean with respect to human intelligence? And I think every time we do something like this, it strikes that chord. And we learn a little bit about computers and a little bit about ourselves and the process. So I think, like chess, the idea of approaching a problem like Jeopardy resonated as an important grand challenge to pursue. But the two problems are very, very, very different. And in some sense, if you compare and contrast them, you think about chess, right? A finite, well-defined search space, limited number of moves, all the symbols are sort of completely grounded in a mathematical model. And when you sort of step back and reflect on that, it's a bigger wonder that humans can play it than that machines can play it, frankly. But when this whole world started, we thought, the whole world of artificial intelligence, we thought, well, but the people who play chess are just so darn smart. And it seems so hard, to the average human. This is just amazing to see a computer play chess. But when we think about language, though, language is sort of completely different. It's sort of on the completely other end of the spectrum. Humans are prolific at it. We do it really, really well. Computers are horrific at it. Computers don't understand language. There is no well-defined formula. There's no clean interpretation of what words actually mean. They're only grounded in human cognition and human experience. One of the stories I like to tell about this, I have two young daughters, and a common experience in the Ferrucci household is for me to be screaming down at them saying, come down here, you have to see this. This is really, really interesting. I'll be doing some sort of experiment in the sink or something scientific that I want them to learn about, whether it's programming a robot or looking at fluid dynamics or something. And at the time, I guess my daughters were 9 and 7. And come down here, this is really, really interesting. So they hear this repeated over and over again. This was a common experience. And so one time my 7-year-old stopped at the top of the steps and she said, Daddy, interesting things are boring. And what struck me about that was she wasn't really making a joke. Her experience with the word interesting was actually a boring experience. And this was the meaning she associated with the words. We have to understand that the words do not have inherent meaning. The meaning is acquired through context and through association with a common experience. Well, computers aren't human. So where are they going to get that association? Where are they going to get that mapping to that common experience from? So this is a much different kind of problem for a computer to take on. And one way to start to think about this, when we think about question answering, it's ultimately there are two different ways we think about computers doing this. So I just described to you one way, which is computers really understand things the way humans do, very, very hard. But the other way people think about computers is that in the form of databases. You put stuff in and you get stuff out. You put your social security number in and you get your address out. And this is a common way people kind of think about computers. And in fact, as I started to talk to more and more people about this project, I found out that the audience was split, it's kind of bipolar. On one end of the spectrum, you had people who heard about this Watson thing and they thought, well, what's the big deal? Computers know everything already. And on the other end of the spectrum, people thought, oh my God, this is scary. Watson's going to take over the world. This Skynet, we're all dead. So there was this, this bipolar reaction. I think in reality, many people sort of have this opaque understanding of what's really going on inside a computer. And at one point, a radio show host interviewed me. And he said, so let me get this right. So the computer's going to play Jeopardy, and the way it's going to work is you're going to put all the answers in a spreadsheet, and then you could put all the questions in. And then when the clue comes up on the board, Watson's going to speak the answer, right? I said, no, of course not. Of course, it was a radio interview, thankfully, because if it was a TV interview, they would have seen me go, So I said, no, of course not. Not only doesn't it know the answers, it doesn't even know what questions it's going to get. And so the host said, well, then how do you do it? And I said, exactly. That's exactly the issue. How do you do it? And this is kind of helps demonstrate that. Imagine that you had a database and and you had this question, where was X born? And you knew ahead of time that you're going to get questions like this. And you knew that the way to answer them was to look up whatever was bound to X to the person column, Albert Einstein, and you pull out the answer under the birthplace column, Aoun. But imagine instead you didn't know what question you were going to get. You didn't know what it meant. You didn't know how to look it up in any particular database, and you just read a bunch of text. And you read, one day from among his city views of Aoun, Otto chose a watercolor to send to Albert Einstein as a remembrance of Einstein's birthplace. The answer's in there, but you have to do a lot more work now. What are the people? What are the places? How does it relate to the question? What does the birthplace have to do with being born? There's a lot of contextual background knowledge that goes into interpreting that language to understand what it means relative to the question. Here's another one. X ran this. Well, if I programmed the computer ahead of time to bind Jack Welch to X and knew that I would look up Jack Welch in the person column and the answer would be in the organization column, it's pretty straightforward. And that kind of processing drives so many computer applications, these database processing. But if it just got this string, these series of words, letters, X ran this, I don't know what it means, or how to map it to a database, or that a database even exists that contains the answer. But I just looked at a bunch of documents, and one said, if leadership is an art, then surely Jack Welch has proved himself a master painter during his tenure at GE. I may be able to infer from that Jack Welch was a painter at GE rather than the CEO. So language is hard. Understanding it in context and relative to questions are difficult. Here's some examples from medicine, just to give you a sense of the way humans deal with complexity and subtlety of meaning. So we have, food would get stuck when she was swallowing versus swallowing difficulty versus food gets held up versus can cause food to move slowly in the esophagus. I mean, all these things mean the same thing, but very, very different ways to express it. If we look at sudden onset of chills, is that different from chills? Is that different from a cold? Fever, temperature, high temperature, are they the same thing? How are they different? Fever after acute symptoms subside. All these things have subtle differences in meaning. Flank pain versus lower back pain versus kidney pain versus pain between the upper abdomen and the back. So causation, location, terminology, chronology, all affect the meaning of these various phrases. So if you want to help a doctor diagnose a problem or help choose the right treatment for a patient, and what you have in front of you of mounds and mounds of literature and documentation and notes, what does it all mean? How do you confidently understand what's being expressed in that content? So along comes Jeopardy, and Jeopardy, this is a hard problem dealing with language, and Jeopardy as a challenge says, you know what, you can't do this today. And even though this is a television quiz show, this is actually going to challenge and drive the technology along a number of key dimensions. One, broad open domain. If you're standing, it's a direction you should look to check out the wainscoting. Anybody? Down's the answer according to Jeopardy. Looking for a direction. How would you model a direction if you're building a database? North, west, east, south, all the degrees around a compass, up, down, right, left. There's another Jeopardy question that says, this is the direction of fabric, blah, blah, blah. I don't know the whole thing. The answer is grain. Would you have thought to model grain as a direction? So it's hard, right? It's hard to imagine all the different ways to represent questions and how they relate to data. In cell division, mitosis splits the nucleus, and cytokinesis splits this liquid cushioning the nucleus. Anybody? Cytoplasm. You got to. If you know it, you got to jump in quick. The first person mentioned by name in The Man in the Iron Mask is this hero of the previous book of the same author. For 1,000. D'Artagnan. Of the 4 countries in the world that the U.S. does not have diplomatic relations with, the one that's farthest north, 2,000. North Korea, that's very good. So interior design, yeah, I'm not paying the 2,000, but so interior design, cellular biology, classic literature, geopolitics, complex language. The questions are asked in all sorts of different ways. You have to be really good at it. You have to get a very high precision. You have to know a lot. And one of the really important and interesting challenges of this game that drove the technology in, I think, a very, very important direction is you have to have an accurate confidence. In other words, you had to know what you know. If you buzz in and answer the question and get it wrong, you lose the dollar value associated with that question, and you give your competitors a chance to answer that question. So there's a big risk and buzzing in and not knowing the answer. So Watson would have to keep its mouth shut when it actually doesn't know, unlike most politicians. So you have to be able to compute a probability that your best answer is in fact correct. And you have to do this all really, really quickly. So we looked at about 20,000 randomly sampled Jeopardy questions and looked at what are they really asking about. And we got this very long tail phenomenon. So things like songs and products and substances and insects and founders and senators and diseases and novelists and heroines and vegetables. And they're all contributing very, very little to the entire space of questions. So if you sat there and you said, I'm going to anticipate all questions about a particular topic and model all answers for that topic, you're going to get nowhere fast. Because what would you pick? Even if you attacked the entire head of the tail, you'd cover less than 10% of the data. I mean, you wouldn't even qualify for Jeopardy. 13% of the questions don't refer to anything. They just say this or it. So like this one, Lincoln Logs. Treasury Secretary Chase just submitted this to me for the 3rd time. Guess what, pal? This time, I'm accepting it. Anybody? Resignation is the right answer. Now, I wonder whether or not you actually knew the historical fact or you used something that I like to call plausible inference. So who knew the historical fact? Who used plausible inference? Yeah. So good. I didn't even have to explain plausible inference. So you look at it, you say, well, what kinds of things are submitted? And what kinds of things are submitted by a government official? And what kinds of things are submitted are even worth talking about or worth asking a question about? So all this kind of contextual information allows you to come up with a plausible idea of what the answer is. And in fact, in this case, you got it right without even knowing the historical fact. Well, Watson kind of has to do the same thing. He's got to use context because it's not always the case that anybody actually wrote something like this in exactly that form. So you're going to have to generate possibilities and then look for evidence that might support those possibilities. That evidence might look fuzzy to you. Right? So because again, you're not looking this up in a database. So one of the things does is Watson comes up, given the context, plausible inference. Now context is so important here. So we were giving this to this presentation to a 6th grade class. And we asked them the same thing. And we were testing their history, but they used plausible inference. And they got a different answer. Say that the right answer was a friend request, because in their sphere of experience, that's what they submit. They submit friends requests, not resignations. So how do we learn about context? How do we learn how words are used? We can't sit there and write down every possible phrase and every usage of every word. But what's new about the world, or relatively new about the world, is there's a lot of text in electronic form out there that we can start to analyze. So we take large volumes of text and we do syntactic analysis, like you would diagram a sentence and what's the subject, the verb, the object, the prepositional phrase, the object of the preposition, and so forth. And then we do some semantic analysis over that, and we say, well, what, can we identify officials and inventors and things like that? And then we aggregate, we do statistics over that. How often is this kind of thing said? And can we aggregate those statistics? So we can learn things like inventors patent what? They patent inventions more often than not. Officials submit resignations. They may submit other things, but it seems like they often submit resignations. People earn degrees at schools. And you say, well, geez, this obvious stuff, it's obvious for you, but we're not writing all these things down. We're trying to get the computer to learn all these simple axioms about common sense knowledge from analyzing text. Because you can ask a question, where did this person get their degree? And often in the early days, Watson would answer with a state. But that's not really what you expect. You expect a school. How would you know that? Well, you know that by doing this kind of thing. Fluid is a liquid. Liquid is a fluid. Vessels sink. But people sink 8 balls in the game of pool. So not only do you need to look at the syntactic and semantic analysis, you need to also represent a contextual analysis. So under what context are you more likely to sink a vessel than a cue ball or something? So we do this kind of thing. So here we had that question, cell division, mitosis splits the nucleus, and cytokinesis splits this liquid, cushioning the nucleus. No, we didn't hire a biologist to sit down in there and model all biological things, right? We would, if we did that, we would have gotten what? 0.001% of the data in Jeopardy. This was not the way you can approach the problem. So what we did was analyze this. We do a syntactic and semantic analysis of it, and we do searches and generate all possible answers somewhere in the area of the domain: organelle, vacuole, cytoplasm, plasma, mitochondria, blood. And then we look for evidence that some of these answers are more right, or there's more evidence supporting one than another. So, for example, one dimension of evidence is the answer even a liquid? Well, so I want to find out, to what degree do I believe cytoplasm is a liquid, organelles a liquid, vacuoles a liquid, and so forth. And so Watson goes and searches for evidence. Well, cytoplasm is a fluid surrounding the nucleus. Well, that's really good, but is a fluid a liquid? Watson doesn't know that either, because we didn't pre-program any ontologies. We try to learn things from existing resources of knowledge. So there are many algorithms that actually try to determine this. One of them looks at a taxonomy called WordNet, which is a taxonomy that's been under development for years at Princeton. And one of the algorithms consults that and says, I got this token fluid and this other one liquid. Is a fluid a liquid? It's not, because in a true taxonomy, fluid is considered more general. So liquid's a type of fluid, but a fluid's not a type of liquid. So it says, sorry, can't help you. But another algorithm goes and looks at that mine data that I just talked about, that we just analyzed by large volumes of naturally occurring text, and it actually gets some signal that fluid is in fact a liquid, because the way people use words is they use them interchangeably. Fluid, liquid, tomato, tomato, right? They're not following a strict physics taxonomy. But why would Watson trust this over that? And that's a very interesting question. It trusted through a process we call training, or statistical machine learning. So what happens is we let all these algorithms run over many Jeopardy questions and answers, and the machine learning algorithm learns that this is often helpful. So it trusts it. This is helpful too, but this is helpful as well. Now, if I was training on physics tests, this would likely be more helpful than this. But if I'm training on Jeopardy questions, it turns out that this is helpful as well, and I could trust it, I could boost my confidence in cytoplasm. There's a lot of key ideas going on here, right? It's like, if you're answering questions or talking to somebody, but you switch contexts, you start interpreting words and phrases a little bit differently. You see how good I am at language. And you start weighing that information differently. Well, that's exactly what's going on with Watson. So by training on the Jeopardy data, it's learning how to weigh the information it's getting from different sources differently. So in May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India. Anybody? Vasco da Gama is the right answer. And what I want to point out to you in the next two slides is the nature of evidence, right? You could look at this as keyword evidence. In other words, let me find some support for an answer using keywords, and I might get this passage. In May, Gary arrived in India after he celebrated his anniversary in Portugal. So lots of keywords in common. It suggests Gary's the answer to the question. And Gary's an explorer, right? After all, you can imagine the next sentence said, Gary returned home and explored his attic looking for a photo album. Gary is the subject of the verb to explore as evidence that Gary can be considered an explorer. But is it really the explorer in question? Unlikely, right? So now, same question, but now I have on the 27th of May, 1498, Vasco da Gama landed in Caput Beach. The only keyword it has in common is May, but this actually contains the right answer. How am I going to get there? Well, first of all, I have to be willing to look far and wide and consider evidence that doesn't necessarily contain a whole bunch of keywords. And then I have to be able to make the inferential leap with temporal reasoning. 400th anniversary in 1898 refers to 1498. Statistical paraphrasing. Now, there's the idea that landed in and arrived in occur in similar contexts. So there's a reason to believe they might mean the same thing. Geospatial reasoning. A database tells me if I'm in Caput Beach, I'm in India. So with a collection of algorithms that can try to match these various parts of the question with evidence, I can get some confidence that Vasco da Gama is the answer. I may find a lot of evidence that Vasco da Gama is an explorer, more so than Gary is. So what I have here is I have evidence, hopefully more evidence or more believable evidence, evidence that scores higher, that Vasco da Gama is the answer. Am I 100% certain? Absolutely not. Because every one of these algorithms can make mistakes, both in interpreting the language and in the fact that they're probabilistic in nature. So I have to combine all these probabilities, and hopefully I get more evidence that Vasco da Gama is an answer than Gary is. When 60 Minutes premiered, this man was US president. Anybody? So what's interesting about this, it's unlikely someone wrote, when 60 Minutes premiered, Lyndon B. Johnson was US president. So often someone making a query doesn't query exactly in the form that other people wrote the information. So you have to decompose and dissect the question down, and Watson will do this and say, okay, I'll get when 60 Minutes premiered, 1968, I'll formulate a new question, ask that, see if I can get a confident answer to that. First of all, it has to know that it can't answer the first question directly, but in fact it's worth breaking it down into sub-questions. So Watson will do this. Does it mean it gets them all right? No, it doesn't. But it does that. Shirts, TV, remote controls, telephones. Answer? Buttons. Isn't that amazing? How'd you know that? That's what Jeopardy thought too, but we ran this through the computer using a technique called spreading activation, and we got things like plastics, oils, things made by man, things under my couch. But, you know, Jeopardy agreed that buttons was the answer, unfortunately. We call this the missing link. On the hearing of the discovery of George Mallory's body, he told reporters he still thinks he was first. Edmund Hillary is the right answer. What's interesting, the relationship between these two things is in both cases there's a missing link. In the second case, so the missing link's not the answer. The missing link is Mount Everest. So you actually have to analyze the question and figure out, how do I find the intermediate clue that helps me get from George Mallory to Edmund Hillary, the person who thought he was first at Mount Everest. So this is a complex combination of both natural language processing and reasoning, making inferential leaps that you have to do to answer questions like this. So how good are humans at this task? In other words, if that was the Jeopardy task and you see kind of the nature of the challenge we face, what was the competition like? So this graph characterizes the competition. Every dot on this graph is an historical and actual Jeopardy game. And what I'm plotting is the winner, the performance of the winner of that game. So if you look in the center of the green cloud, the performance of the winner, if you trace it down to the x-axis, is answering nearly 50% of the questions. That means they're confident enough and fast enough to buzz in and answer 50% of the questions, nearly 50%. And if you look to the y-axis, they're getting between 85 and 95% of those questions right. Very, very high precision. So they're very confident, they're fast, and they're getting the questions they think they know, they're getting between 85 and 95% right. The red dots are Ken Jennings. Ken Jennings won 74 games in a row, and on average, he was acquiring 62% of the game. Right? So in other words, he was so confident, so fast, he would get to answer first 62% of the questions. So you could just imagine he just assumed he knew all things. And unfortunately for his competition, he was about right at that. He did on average about 92%. But there are games here where he's answering, of course, this depends on the competition, but you know, there are games where he answered 81% of the game. I mean, it's just watching Ken Jennings answer questions. You don't even know who else is playing. There are other games, you know, where he got them all right, but he only answered, you know, 42%, for example. So this was the question answering system. We had a state-of-the-art question answering system. Had many of the state-of-the-art techniques in it. We had good partners, university partners, and other industrial partners as we developed this. We turned it on the Jeopardy problem and got this confidence curve. The way to read this is, if it had to answer the 5% it was most confident in, it would get 47% right. As it had to answer more and more questions that it was less and less confident in, it did worse and worse, plateaued at about getting 15% right. This left, of course, a huge gap. And this is what we took on in 2007 to try to make that leap. And this is what I bet my career on, and it worked out. But might not have. In any case, what did we end up with? How did we end up solving this problem? This gives you kind of a high-level view of what we call the deep QA architecture, which is underlying the Watson system. And the way to think about this is it does that kind of analysis that I alluded to earlier, which is it analyzes the question. It does that kind of syntactic and semantic analysis. And based on its interpretation of the question, it does many, many different searches against lots of different sources. And it may come back with 100 possible answers, 100 candidate answers, possibilities, hypotheses. I think this might be the answer, like organelle or vacuole or plasma or mitochondria. And then for each one of those, it spawns an independent thread. So these become independent competing hypotheses in the system. So for each one, it spawns an independent thread and says, let me see if I can go collect more evidence to support that answer. And so it goes off and collects evidence. And so for each answer, let's say it goes and gets 100 pieces of evidence. So now it has 10,000 evidence answer pairs. Right? For each answer, I have 100 pieces of evidence. And now for each piece of evidence, like imagine a piece of evidence is like a sentence or a paragraph that might support that or refute that that answer is in fact a correct answer to that question. Now for each one of those answer evidence pairs, I now have about 100 different algorithms, actually several hundred different algorithms that analyze that evidence answer pair and come up with a score. Say I give it a, a 10%, I give it a 60%, I give it a 50%. These are all like independent experts, if you will. How good they are as experts is a separate question, but they all think they know something about the likelihood that that evidence supports that answer. So now I have millions of scores, and I have to balance them now. And that's where the machine learning comes in, because I'll run the entire system, and I'll have all the experts put their input in, and then because I know on the training data, I know the right answers and the wrong answers. Statistical machine learning will now compute a function. It'll figure out the weights, how much to trust each of those experts. Under these conditions, I trust that person 50%. Under these conditions, I trust that expert 70%. And it combines all those weights and then combines them, comes up with a final confidence, says, I have the most confidence in this top answer, cytoplasm. Maybe that confidence is 70%, maybe it's 80%, maybe it's 40%. So during the game, there was a threshold. And if that confidence was above a threshold, Watson would want to buzz in and answer that question. If it was below that threshold, it would stand back and say, I don't want to take the risk. And that threshold might change during the game. If it was way ahead, it would say, I'm not going to answer unless I'm 95% sure. If it was behind and trying to catch up, it might answer with only 40% confidence. It wasn't like we just took that architecture, figured it out, plugged it in, and we solved the problem. This took 4 years to develop algorithms and advance them to the point that Watson was able to perform as well as it did on that test. And I wanted to share with you very quickly what the growing pains were like. This is early versions of Watson. So the American dream, decades before Lincoln, Daniel Webster spoke of government made for, made by, and answerable to them. Early version of Watson. What is the answer? People. Watson? No one. New York Times headlines, an exclamation point was warranted for the end of this in 1918. What was it? Great World War I, right, is the correct answer. Watson, a sentence. Now, I mean, a sentence, exclamation point ends a sentence, doesn't really matter what year. So that's not so stupid. In 1994, 25 years after this event, one participant said, for one crowning moment, we are creatures of the cosmic ocean. Anybody? Moon landing, that's right. Watson, the Big Bang. So, you have to understand, the point we were in with project, when it answered with the Big Bang, I said, oh, it answered with an event. That's fantastic. What about this? Queen's English. Give a Brit a tinkle when you get into town and you've done this. Call him on the phone. Watson, you're in it. That's what I thought the answer was. But yes, call on the phone. And this one I can't really explain. Father of the nicknames. This Frenchman was the father of bacteriology. Anybody? Pasteur, right. Watson, very early version of Watson. How tasty are you is my little Frenchman. So, right, it's not like you just turn this thing on and it works. So we went through a long process of really advancing this. I'm going to go through the next series of slides quickly, but I just want to impress upon you that over those years we did over 8,000 documented experiments about where we would try different algorithmic techniques and different ways to integrate them and combine them to try to achieve good enough performance. We went through an entire process where we would train, we would judge, we would teach, we would do error analysis, and then adjust and invent new algorithms and plug them into that architecture to drive that performance upward. We had tools that allow us to document these experiments, drill into the performance on the experiments, sort of understand. This is just to give you, I know you don't, it's hard to understand this slide, but just to give you a sense, here's a question with many different possible answers, and there are hundreds of algorithms that are contributing tiny, tiny little influences on what the right answer and wrong answer is. So this is comparing Argentina and Bolivia to the question, Chile shares its longest land border with this country. This list goes on over 100 different algorithms, and they're all contributing tiny little amounts to their belief of which answer is right or wrong. So we would combine this information up so that even just the humans can understand it, and we'd classify the algorithms as geospatial or passage support or popularity or classification, things like that. So we can look at graphs like this. There's a Bethel College and Seminary in both cities. You'll find a Bethel College and Seminary in this holy Minnesota city. The problem was there's a Bethel College and Seminary in both St. Paul, Minnesota and South Bend, Indiana. And when you bubbled up all those algorithmic contributions, you find that it in fact knew that St. Paul was in Minnesota and a better answer for location information, but all the other data overwhelmed St. Paul, and it was in favor of South Bend. So this kind of graph would tell us we need to figure out how to make Watson pay more attention to location information. Natural response by humans. But how does it understand what's going on here? So we'd have to learn how to do that. So this would allow us to bubble up huge amounts of data to figure out how to react to the errors. Another way humans get this is they look at it and they think, wait, holy, which city's more holy? So it's a pun. So someone actually created a pun detector and put that into the system. And it gave more positive weight to St. Paul than South Bend. But then, of course, Holy Cross, Minnesota was a competitive answer because Holy Cross is more holy than South Bend. So with that architecture, with those techniques, and with that methodology that we pushed on for 4 years, we went from that baseline performance all the way to a performance slicing through that winner's cloud. And in fact, got a little bit better than that, but that measurement was taken in November 2010. We played the game in January 2011. And this is on blind data. This is on data that neither the developers nor the system, of course, was ever exposed to. Over 200 games worth of data, 12,000 questions. Would it win every game with that performance? No, it wouldn't. It would depend on the competition. But you can compete against grand champions with that performance. It wouldn't necessarily win every game. We went into that final game with a low, about 72% chance of winning. That's a 28% chance of me losing my job. So the good news was we won. It took about, that computation that I described to you, took about 2 hours to answer a single question on like a 2.6 gigahertz machine with 16 gig of RAM. And the Jeopardy producers kept telling me 2 hours is just going to make for a very boring Jeopardy game. It took 2 hours per question. So we had to scale that out. We actually scaled it out because it was an embarrassingly parallel computation. That's why I have that graph where the arrows keep splitting. Every time those arrows split, I can actually spawn an independent thread and run it on a separate processor. So we actually deployed this on 2,880 cores of Power 750 with IBM chip type, an IBM machine, and with 15 terabytes of RAM. And it never went to disk because it would have been too slow if it went to disk. And with that configuration and scaling that system out, we were able to answer in just under 3 seconds, which was fast enough to compete on average. And in fact, in the actual game on television, Watson lost an entire category because it answered too slowly. It knew every answer with 95% probability, got it right, and it lost to the humans because it couldn't figure out the answer or the confidence fast enough. But in spite of that, we won the game, and that part of it is history. What is Watson? I just want to spend the last few minutes just talking about what is it, because we didn't do this to generate a revenue stream winning on the Jeopardy quiz show. We did this really because we believe that there's an opportunity for technologies that do a better job at deeply understanding and analyzing natural language content. Because some problems you can solve with search, shallow understanding, low precision, give me back a bunch of documents that contain my keywords. Other kinds of problems where if I can build a database and I have very structured queries. But in the middle, there's this whole class of problem that says there's a lot of valuable information in those documents that if I could understand that language a little bit better, I can actually do a better job at solving that problem, basically building decision support tools that leverage that kind of knowledge. Lots of different areas, from healthcare and life sciences, tech support, enterprise knowledge management, government. One of the really interesting areas for us is medicine. Imagine I showed you what those bar graphs, like evidence profiles, we call them evidence profiles, but it's not just about the answer and the confidence, it's about the evidence. It's like, why that answer? Like you're giving us 3, 4 answers, why? Right? So I could break that analysis down and say, well, I read a bunch of things, and from a symptoms perspective, I like this answer this much. From a family history perspective, from a personal history, from medications findings, So you can start to analyze all the evidence you've collected and scored in terms of things that are meaningful to a human user. And then I can go further and I can consider many different hypotheses. I can get the evidence profiles for the different ones, renal failure, UTI, diabetes, influenza, based on all the input I'm getting from the doctor's notes, to medications, to the EMR, to volumes of text, journals, references, and databases. And then once I produce those evidence profiles, I can then sort of display them and help doctors and healthcare professionals understand what's out there in the literature and how it relates to that case. And here's an example of not only am I showing you the evidence profile, I'm actually showing you the evidence, the textbook or the website or the journal that supports that the symptom evidence supports a particular answer. So now you can drill into basically what Watson's thinking and why it's coming up with those numbers and those confidences. But of course you have to adapt it. You have to make it smarter. Out of the box, if I take the Jeopardy system out of the box and I run it on medical data, questions like these, this inflammation is characterized by nasal mucosal atrophy and foul-smelling crust in the nasal passages. Oh, let's have some. Anyway, skin rashes, Lyme disease, so forth. Out of the box, here's the confidence curve that it got on these kinds of questions, very different than Jeopardy questions. Going through this process again, we actually were able to move it from this line to this line by just adding more relevant content. Well, this is about medicine. Let's get some medical content in there. Not even a whole heck of a lot, actually. Then by training on those questions. So weighing all those various experts, recalibrating them in a sense, based on looking at training data, we actually took this jump from here to here. Then starting to do failure analysis. So I didn't even do any failure analysis yet. Now starting to do failure analysis and adapt the algorithms. I'm getting a better confidence curve, which on 50% of the data, I'm getting 80% of them right. So rapidly being able to adapt this technology to new domains is how you're going to scale this into a profitable business. And this is very much what we're focused on now. So there's a lot of work to do, from going from specific questions to kind of rich problems, being more interactive. In Jeopardy, you can't ask a question back. You can't say, well, wait a second, if what you mean by APB is all points bulletin, then my answer would be this. If what you mean by contraindicates is I shouldn't use, then my answer would be this. You can have that dialogue. Watson knows actually where it's failing to understand something and can generate those questions. So we want to be more realistic in terms of generating dialogues. And ultimately, that process of adapting to a new domain has to scale. It has to be more efficient to do. So that's another direction. So this gives you a sense of where we were with Jeopardy, specific questions, answer in, answer out, just answers and confidence in a batch training process. We need to look at rich problem scenarios, interactive dialogue, evidence profiles that drill down into the evidence, and a continuous training and learning process that becomes more efficient over time. So this is the direction we're taking the technology. So anyway, I'll stop there. Thank you.
David, thank you. Thank you, David. We're going to have a dialogue with David now. The rules are very simple. Your question should be shorter than the answer that he would give. Let me start by asking you, actually, David, you shared with me that you had to shrink your team first, and you had a massively interdisciplinary team, and you talked about extreme collaboration. How did you manage that? Talk about how you brought people with different disciplines, different understandings of the world together.
So there was a couple aspects to it. I mean, first of all, there was just a historical intuition. I've been building this team for years, and I was always interested generally in artificial intelligence. So as my career progressed, I was always bringing people in who had different perspectives on the problem. So in some sense, you can think of that as luck, or you could think of that as unintended preparation for this particular problem. But I think it was a little bit of both, that I had a team that had a lot of these different disciplines. Getting them to work together was, on one problem though, was a challenge, because the traditional way things kind of happen, I think also in universities as well as in industrial research centers, is if individuals doing kind of isolated research. So a computational linguist doing their thing, and a knowledge representation reasoning person doing their thing. And a lot of what I had to do was bring those people together and say, you know what, we're going to all work together on one problem. and in fact, even in one room around a common table, so that you get that dialogue and that high bandwidth communication so these people are interacting towards the same goal.
You told me that you mentioned to somebody who mentored you over the years that you were very lucky, and he told you, no, it's not luck. So now you're telling me it's pure luck. I don't know what to believe anymore.
No, when I actually, he was complimenting me, saying it's amazing that you were able to do this, and I said, well, some of it was certainly luck, and he had known me for years, and he said, I don't think it has anything to do with luck. And he made that point that when I look at your career, you had been building this team and never gave up on this technology for decades. So you were very well positioned to actually take on this challenge. And he said, so I don't buy it's luck at all.
You also mentioned to me that actually you shopped the project around, and IBM at the beginning, you had to convince people to do it. And could you walk us through this process and explain why ultimately did your manager or IBM buy into this project?
So IBM was initially motivated by the excitement they were able to generate with the Deep Blue project, the system that played chess. And that was very exciting for the company, and it helped bring a lot of attention to the scientific program at IBM. So that was sort of an initial motivation. But at the same time, there were many folks, lead technical people in IBM, who felt that this was way too hard. It was really pure folly. We were going to fall on our faces, and sort of embarrass ourselves. So there was quite an internal struggle that went on. And ultimately, I spent some time doing a feasibility. This is why I reduced the team. I reduced the team because I didn't want to come out and say, I need to invest 40 people in this, right? Because then people say, oh, forget it, right? So I said, let me invest a smaller number of people, do a feasibility study, make a strong argument that I think I could do this. And ultimately, I convinced enough people, not everyone, to make the next level of investment. As I started to succeed, the people who were very much against it either became advocates or left the company. No.
Yeah. Now, we're going to open the floor for questions. Let me start with Matthew. Matthew actually spent time at IBM doing his co-op, and as you know, I mentioned that to you, over the last 5 years, we had over 60 co-ops at IBM, and we have now 500, more than 500 alums at IBM. Some of them are here tonight, so they are here to cheer you and support you. But let's start with Matthew. This is a question that has been coming from Facebook and Twitter. Choose one. Let's go with that. And let me ask everyone, if you are interested in asking a question, we have a microphone. And Matthew, why don't you start?
Sure. And you can also submit your questions online through Twitter with the hashtag #NUSpeakers. So the first question we have is for Dr. Ferrucci. What did creating Watson teach you about the process of innovation?
I have a very, very long answer to that. A lot, much more than I ever expected, frankly, and that's why it's a long answer. But let me see, what's a good highlight? I think that today, particularly in the space of computer science, innovation requires diversity. It requires a lot of different perspectives, a lot of different people coming at it, thinking about the problem differently. But at the same time, it requires a vehicle for that diversity to take effect, to be able to realize the benefit of that. And I think of that as architecture, and that you need a certain investment in architecture and engineering in order to exploit the scientific diversity. And those two things create a tension, frankly. Because when you have a lot of different perspectives, it's hard to get commitment on an architecture that's going to help integrate those perspectives. So you can't go too much in one direction or the other. That is the challenge, and I think the key to this kind of innovation, and we struck a sweet spot there. with this. It was not easy. There was a point in time in the project where that particular issue came to a head. I could not get everyone to converge on a common architecture because of that reason, and had to take extreme measures for that to ultimately happen. And then once it did, it worked.
Thank you.
Thank you. Arvin?
50 years ago at IBM, Dr. Arthur Samuels did a lot of research on how machines learn as part of, as he said, trying to find out how people learned. Did any of his research have any influence on the development of this project?
So not directly. I get this question a lot, but more generally about, did you think about how humans, did you have cognitive psychologists and, did you have people think about human cognition influence the design of this? And directly, no. Indirectly, you would often find in design meetings when we looked at certain phenomena on the data, certain failure, people would think, well, how would a human do this? How would a human do that? So, and it did influence some of the algorithms. Ken Jennings, the Jeopardy player, goes around giving a talk. It's actually better than mine. I'm very jealous. He's quite comical and funny, and he makes a lot of nice, interesting points. But one of the things he says is that, when I first came to play Watson, I thought Watson was this machine. It doesn't do anything the way I do it. And then when he learned more and more about the algorithms, how they worked, he started noticing, but that's exactly how I do that. That's exactly how I do that. So, but it's interesting that those parallels are there. We didn't try to, make it work like a human.
Matthew, let's go back to you. In case you would like to ask a question, please feel free to come to the microphone. Go ahead, Matthew.
Absolutely. Thank you again. So the next question from one of our Twitter followers is, what is your favorite thing that Watson can do? Did it make you laugh?
Watson made me laugh. Well, you saw those questions, so it certainly, you saw those answers, I should say. So it certainly has made me laugh. My answer is going to be a sort of a technical answer because I'm a geek at heart. What it does that's interesting to me is this theme of the architecture was able to take the contributions from many independent researchers and get this holistic behavior that was difficult to predict. You couldn't sit there and say, oh, we know exactly what Watson is going to do here. So you got this holistic system performance that no one algorithm would predict you'd be able to do. And that's very cool to me. I mean, that's very interesting, right?
Thank you.
Hi, Dr. Ferrucci.
Hi.
It's an honor.
Thank you.
I'm Faraz. I'm a freshman student here. I'm actually not a computer science or engineering major, but what I wanted to ask you was how many languages is Watson planning on being programmed in?
You mean human languages or
Programming
languages?
No,
Okay.
human languages.
So it's English now, and there is interest in doing other human languages. I don't know what it's going to take to do that, frankly. I think that comes down to dollars and cents. Theoretically, of course, this can be done in multiple languages, but it's an investment. And at IBM, there's we have a very strong machine translation team that works in many different languages, and there are lots of other people who can contribute to this. And it's really a matter of where the investment drives us. So I don't have a simple answer for you. It can be done. It's work. It really, it's all about where the investment drives us.
Do you think you would go into something like that?
Me personally, I'm not as interested in the multilingual aspects. There are a lot of people who can do that much better than I can. I'm more interested in just making it smarter in the sense of making it be able to do more accurate inference over natural language content independently of the particular language.
Thank you.
David, you mentioned that actually you were afraid to lose your job. You can always apply to be part of this community.
Thank you.
But
Thank you.
And you mentioned that examples of failures, challenges, etc. And my question is that, and you worked with various universities and various academic institutions, could you have done that project in an academic institution?
Great question, and I know that quite a few people are thinking about this, and in fact, I know a few people are writing an article about it, because that question always comes up. And one of the challenges that is perceived is this issue of the incentives around professors having a particular research agenda that they want to pursue, and the incentives aren't necessarily there to work in a multidisciplinary fashion. I mean, my researchers gave up publishing for 4 years. And so the typical incentives of a researcher, which is, get your standard number of publications out that year, was just put to the side. I had to convince not only the researchers to do that, which is hard enough, but I also had to convince the management team, because the metrics used in IBM research, like in academia, are to look at the number of high quality publications. And every end of the year, you got to do your evaluations. And I said, we're not measuring the people on that this year. We're not measuring them on that this year. We have to measure them on the performance of the system against this task we all believe is incredibly challenging. So this has got to resonate in and of itself. And that's kind of an interesting thing, right? Because everyone had to buy in. This is a really interesting and important thing to do. And if you've bought into that, then you're going to accept that it's not about this person's publications this year. It's about, did they take a bite out of this challenge? And on prima facie evidence, this person is doing something important, right?
That's great. We have, yeah, your turn.
Hello, I am a chess player, and I did appreciate the performance that Deep Blue did beat Garry Kasparov, and I was curious how much Watson was based off other chess playing programs and how different it's programmed, because I know that most chess playing programs today are based on decision trees and things like that. And well, this is more based on semantic analysis and completely different type of analysis. I'd wonder, based on that type of analysis, how well Watson would actually play chess, trying to use that.
So
instead.
if you ask Watson to play chess, it would call its brother Deep Blue as a subroutine. Watson can't. So Watson's not based on Deep Blue and not based on the chess playing algorithms. It's a completely different system. But of course, in the full spirit of hybridization, as I said, it could always call Deep Blue to play chess.
Well, the idea is that when humans play chess, for the most part, we do look at more contextual clues in that sense.
That's true.
In a very different sense. So it'd be interesting to see if you could apply it different instead of just doing positional analysis based on mathematics alone.
Right. No, that's a fair comment. Yeah.
That's a good comment. Yes.
I'm a student in computer science here, undergraduate in Northeastern University. I was just wondering, what are you doing from now on? Are you working on expanding Watson, or are you working on some new task, some new problem?
I'm still working on Watson. So, in fact, the entire team that worked on Watson is intact and trying to kind of take it to the next level. Focus on different challenges in natural language processing, natural language understanding. We're looking mostly at the medical space as an application area, but still looking to generalize the techniques. In other words, get it better at dealing more effectively with language.
And then I had a kind of a follow-up question was, how complex are the answers Watson gives? Is it like a one-sentence answer, or could it output like a full paragraph? Or
So in Jeopardy, Watson's answers are essentially, entities. What is the unknown thing that you have this clue about? But we are certainly looking at richer answers that can be sentence-long things that make sense with regard to the question. So it's one of the important directions to go in, and we have good ideas on how to do that. As you get a bigger and bigger natural language statement, it gets harder and harder to be precise about its meaning. So I don't know how far that's going to go. In other words, giving a document as web search gives about documents all the time, but it doesn't claim that the entire document is an answer to your question. All it's claiming is the document contains keywords. The Watson style of doing things is to really understand what that answer means relative to the question, and that gets harder and harder when you're looking at a larger and larger piece of content.
Well,
Thank you. I think we have actually two more, and we have Matthew. In the interest of time, I'm going to ask you not to do a follow-up question. Your questions are terrific. So David is going to stay afterwards for the reception. You can continue the discussion with him. So let's do that.
Hi, David. So my question is, we're very excited about the applications for the future for Watson in the medical field. Just wondering, you said you got your accuracy curve up to 50%. Do you have a timeline for when you think you'll be ready to take the next step in the connecting with somebody in the healthcare field and trying to actually use Watson in the clinic?
Well, so we're already doing that. I mean, I think part of the strategy is to, the way I like to think of it is to get incremental value out of the technology. And even what it does today is going to bring value to the medical industry. And we announced the deal with WellPoint. We announced one with Memorial Sloan Kettering in the healthcare space. We announced one with Citigroup in the financial space. So it's already bringing value, very much in that area where I mentioned earlier, where you need more precision than you're getting out of typical keyword search, but you need more generality than you get out of tailored databases. You need to have more coverage. And I think Watson could already add value in those spaces, and we're building a business out of that. At the same time, we're continuing to try to make it smarter, trying to make it more and more capable. So I think the way to think about the strategy is incremental value. It could help you do some things now. Over time, we'll try to make it smarter, and it'll do more as we go.
Thank you. Matthew, and then.
So one last question from our Twitter followers. So are there any strengths or limitations to the types of data that Watson can work with?
You bet. So, it's the noisier the data is, of course, the harder. When things are nicely grammatical, it's always easier to deal with. Because it's easier to parse it and to understand the syntax and to relate the semantics. When things are noisy, so a good example is reading an encyclopedia is different than reading email. So when data is noisier, it's harder. You can get signal out of email. You can't get as precise signal out of email as you can out of well-structured text. That's an example. But then there's semi-structured information. For example, lists and the kinds of wiki categories and things like that that are very, very, even though they're noisy you might consider them noisy from like a structured perspective, from like a database perspective. Watson can get a lot of value out of that because it looks at it more statistically. So yes, it matters a lot, and you kind of have to understand the nature of the data.
Thank you very much.
Hi.
More of a comment and a lighthearted question. I thought it was really interesting hearing all this stuff about Watson. I was actually here last year when they had us all down to Curry to watch him play Jeopardy, so that was really cool. And I found that really interesting. I was wondering if your daughters finally find something interesting in Watson.
Oh, in Watson, yeah.
Yes.
So
this was one of the interesting things that she did not declare boring.
So my younger daughter, who found me boring, she doesn't find me as boring anymore, but I think for different reasons. Watson, it's interesting when we were. So to answer your lighthearted question, I'll say that my kids are appreciating me a little bit more every single day. And it has nothing to do with my abilities in science. It has more to do with my sense of humor. But I will give you an anecdote that I thought was fascinating. In Watson had that answer panel where it shows you the three, it's top choice with the confidence. So that answer panel ended up on the game because I really, really pushed for it. I thought it was really, really important. It ended up on television because I thought it was really, really important because that helped people think about what was the nature of the computation. Even though it didn't completely understand the nature of the computation, it made people realize, well, this just isn't looking it up in a spreadsheet. And that was very, very important because otherwise people would have walked away with a very different impression. But I had to actually make a very strong case, both internally at IBM and then ultimately to Jeopardy, because that was a big deal for Jeopardy, because that changed the game in some sense. They didn't want to change the game, right? They had a certain kinds of shots, the 3-shot, the 2-shot, the host shot, the clue shot, you know, those kind of stuff. And the audience is supposed to be doing something specific in each one of those shots. When you put that answer panel up there, the audience is doing, they're all looking at the answer panel. So this, in some sense, cognitively changed the game for them. So it was hard to kind of get them to appreciate that, but it was very, very important. And one of the things I did was I took a sample game, one of the practice games, I brought it home to my little focus group, which was my, you know, my wife, my 2 kids, and my mom was there. And I showed them a game without the answer panel. Now here's my 7-year-old daughter. Watson chose not to answer, didn't know the clue. When Watson chose to answer, she turned around to me, and there was no answer panel. She turned around and said, "Daddy, Watson crashed." Which was fascinating because as little exposure as she has to computers, she picked up this notion that if a computer isn't responding, it crashed. It's not thinking, it's not choosing not to respond. Yeah. It crashed. Yeah. Whereas the answer panel told you, oh no, it's choosing not to respond.
Yeah. That's great. Thank you. Thank you. David, I know that you didn't do it for the money, but what happened with the money that you received from Jeopardy? You don't need to answer the question.
Oh no, it was given to charity.
Charity, that's great. Listen, you are a funny guy, and Jennings has nothing, you know, over you, and we're going to make you more funny by asking you to wear this, and I'll wear this Watson.
And you're going to take a picture.
We'll put it better. I mean, yeah, you have to look handsome. Okay, well, thank you, David.
My head's too big for this. Thank you.
Thank you. Thank you. Thank you. Thank you. Thank you. You're all invited to the reception now, and you can mingle with David and enjoy the rest of the day. Thank you all for coming.